not every detail about how it works, but hopefully enough detail about how it works so you can make intelligent decisions. That's the idea. Anyway, good. I see some folks are showing up. All right. And I will mute them all. All right, good. It looks like the usual suspects. And we got a few minutes before class starts here, so let me talk about the schedule. For one thing, spring break is coming up. So I should make sure and notify people about that. I think, yep, no class next week. So we'll do this time, no class next week. And I have a guest speaker. I put out the call for guest speakers and people are answering. So if you look here, the first one is coming. Here, Neil Desai is going to come in from Knoxville over video, and he's a very interesting guy. If you click here, you can see his B-Sides talk from a couple of years ago. He's a very interesting person. I think he'll be very good to have him. And the CCDC, Western Regional CCDC Black team wants to come give a talk to us. So we're still negotiating the date of that. I told him it really ought to be Saturday morning to go in Liz's class. Well, probably in the next week or so, I'll have the date for that. It'll be sometime in April. And another person wants to come, one of my ex-students. So various people are going to come give talks, so that's good. You know, I like to have guest speakers, and so be aware of that. That's a good thing to do. Red versus blue this Saturday at 11. This will be the second one, and we'll have more of these going by for the rest of the semester. Now we finally finished all the real competitions, so I can do this what I'm developing, and we'll see if we can make it fun. The goal is to make it not only fun to do, but fun to watch, which Kaz is helping with. Kaz made a much prettier scoreboard. So that's a step towards making it more fun. Anyway, it's supposed to be, everybody's welcome, it's extra credit, so it's not supposed to be terribly long or terribly difficult, much simpler than CCDC. And there is no prize, so anyway. And we're gonna go off and pose for pictures with the Board of Trustees on Thursday. So make it there if you can, hopefully. This is a big, big deal. This may save our cybersecurity program. I mean, if we impress them enough, they might go cut somebody else instead of us. We'll see.
Yeah, but who else is making notoriety for the school other than us?
Well, yes, they're making a big deal out of that trophy. The gold trophy really impresses them. So that's
classic golden business.
It is. It's like the bling really does it. Anyway, let's see if there's something. The second one was the transparent trophy, and that I think was actually the bigger accomplishment. Oh, you mean last year?
No, this is
right. You won two in a week. 1 week you won first place in the little local competition, and the next one was second place in the regional competition. And both of those are big accomplishments, but I think they value the first one more because the gold trophy looks more gold.
And it's the mayor's cup.
It's the mayor's cup. Yeah. Anyway, this is politics, right? I mean, there's what you really did, and then there's the appearance for management. And you need both. And now we're in the position of actually having done something good and having something to show management. The fact that the two don't exactly match up is not very important. All that matters is you guys are good, they should give you more money, and they have something they can see to help them understand that. So it's, anyway, this was pretty interesting stuff. And I thought that was pretty interesting. And I'm not quite sure what to make of this one. Anyway, here's a few things that are kind of fun. Let me see if I can somehow get this junk out of my way. So the EFF has contacted, there's these automated license plate readers all over the place, and they're put up by third-party companies, and they all tell you that they are not letting everybody have the data, and they're just lying. And the EFF managed to contact people and said, are you handing this data over to the Bureau of Immigration or something? They said, absolutely not. And then they did a Freedom of Information Act to the other agency and totally found out they were. So it's not too surprising if you do political activism that they're totally lying about this stuff. These readers are keeping track of everybody. They have an incredible database of what everybody's been doing, where every car has been. And it's pretty much just wide open. They're just delivering it by concealing who they're giving it to and not getting any kind of permissions or privacy protection or search warrants or anything for it. Like any other new technological thing, they're just using it however they like in sort of the absence of any oversight or controls. And the EFF is, as usual, on the job disclosing this stuff. So hopefully there will be some sort of regulation or limitation put on that. This guy is, I think, the CEO of JP Morgan Chase. And he says that they're cruel to poor people. And he says his response is he's going to quit demanding high education to get jobs. He said people should just go to community colleges, and that should be enough of an education to get a job, which is a pretty interesting position. And I don't know where he get this idea that people teach anything good at community colleges. He must be a nut. Anyway, and so Cloudflare has been testing to see how many people are man-in-the-middle in HTTPS, and the answer is 18% of all the traffic on the internet is now man-in-the-middle over HTTPS, far more than people thought. And so they discussed the various types of man-in-the-middle attacks that are happening and whether they think they're malicious or not. But a lot of people.
They tell they're man-in-the-middle?
Oh, well, you can always tell with HTTPS because they have to change their certificate.
Oh, so. Yeah.
And so they, in principle, should be putting error messages, but I think many of them have ways of avoiding that. So that the simplest one, of course, is where your company puts up a proxy and they man in the middle, and then they put an extra trusted CA on all your devices. But there are many other techniques, and they explain them here. So it's surprising. I didn't know that many people were intercepted. Yeah.
Is China and their complicated, firewall part of that?
I don't know if China man in the middle is the HTTPS. I would imagine they do because the China government is a trusted CA. So they could totally do it. They could totally sign everything, and your browser would fall for it unless it was Chrome going to one of the top 1,000 websites. Chrome has effectively implemented certificate pinning to the top 1,000 or top 100 websites. It knows who the certificate should be from. So if China is signing Google, Chrome won't fall for it, but any other browser would.
So
yeah.
Firefox can implement pinning?
I think what the other browsers are doing, see, Google Chrome had it first before it was a standard. The other ones are now implementing HSTS. So the sites that add the HSTS header to their website tell the browser to memorize who signed the certificate, and if it changes, then regard that as a problem. That's the modern way to do it, and many browsers support that. So websites that are alert enough to put that tag on their header, you do have some protection, which is basically the same protection you have with SSH, where it's not that, where the first time you connect, it says, do you recognize this server? And it'll warn you if it changes. So that's pretty good. That's what most people seem to have found to be like the usable version of certificate pinning. Anyway, so here's a list of skills for Red Team, which is sort of interesting. I thought it was pretty basic, but anyway, he talks about this stuff. This is 124. And Putin has a strong rule against fake news. Apparently they always have. The news is heavily censored in Russia, but apparently now they have an extra layer where he can just veto news and call it fake without any trial or court order or anything. So this is certainly what everybody wants done here, apparently. All right. So anyway, let's talk about authenticated encryption. And then we get a week off and hard problems. So I'm really pleased to learn something. By the way, I just thought I'd show you something here, which years ago I ran Wireshark and I saw all this STP traffic on the network and I wondered what it was. And it wasn't until I took Cisco that I learned what spanning tree protocol was. And in the same spirit, I've often wondered what all these Cipher suites are. If you run Wireshark and you sniff, and then you make an HTTPS connection to somebody like, say, Bing.com. Okay, so now I've made an HTTPS connection to Bing. So if I filter for, say, DNS, and then I should be able to find a query asking about Bing, I would think. Yeah, here we are. For some reason, this column is way too wide. Go away. I don't know where you're asking. Get lost. Okay, here's Bing.com. So that's the packet that went to Bing. So now if I remove the filter, I want to look at the packets right after that. And you will see, okay, so I do a DNS query. I get a reply telling it where Bing is. Now I'm going to do a TLS handshake with Bing, I would think. And I am here, the client hello and all this jazz. So if I go to, say, the client hello and right-click follow TCP stream, I'm hoping I will see the list of Cipher suites. There's Microsoft, there's Bing, there's a bunch of websites that are signed, and someplace in here there is a list of Cipher suites, and I think there is a way to see them in Wireshark, but I might be a little too, the client hello, the server hello. One of these is going to list all the available ciphers. And yeah, here we are. I think it's down here someplace. Handshake. Yeah, here's the Cipher suite that it's actually decided to use. Transaction layer security with elliptic curve, I think, Diffie-Hellman exchange. Maybe that's not the elliptic curve. I'm not sure. RSA with AES-128, Galois counter mode, SHA-256. As you go through this class, this stuff turns from gibberish into meaning more, which is one thing about it. And I think it was back here. Yeah, this is what I was hoping. One of these had a whole list of available algorithms. And here you go. Signature algorithms and exchange modes and padding. And there's one of these are supported groups and ciphers. One of these things had a whole list of supported ciphers. And I may not be able to do it here. There are cipher suites here. This is what I wanted to see. There. See, what happens is when you do a TLS handshake, you do SYN, SYNAC, ACK for port 443. Then you ask to tell the server, okay, I want to make a secure connection, and you have to tell the server what you can talk. The browser version and the operating system version limit this. So these are the various ciphers that my browser can support. And this is Firefox. So it supports AES-128, Galois counter. Here's the Chata, which is in the book, which is a newer one. It supports all these things. Then the server chooses one, and then you settle on one. So you tell it what you speak, and the server says what it speaks, and you see if you have a language in common. And anyway, I just thought it's interesting to see this, because this stuff should all be beginning to make sense.
Oh, I see. Triple S right there.
Yeah, triple des is an option, as I think a signature. And remember, triple des is okay. Single des is bad, but triple des is reasonably secure. Where is triple des?
At the bottom?
Oh yeah, RSA with triple des, yeah. And this is, and if I had like a virtual machine with Windows 95 and IE3 or something, have all these old 40-bit modes and stuff, and that's why you specify at your server which certificates you will settle for, and when you take away the old ones, you lose really old clients. So a lot of people just haven't updated their server certificate in many years, so it in fact supports extremely low grade encryption keys. And if I man in the middle you, before you do the HTTPS handshake, I can alter this information and cause you to settle for a low encryption mode. So it is a bad idea to have any mode supported on your server that's not safe, because it's possible to trick people into using it. And that's why the cryptology community got so angry about people like the export grade encryption, when they forced everybody to ship Microsoft software and other software with broken old ciphers, because now that was an alternative on the servers, and there were ways to trick people into using it. It really should be nothing offered to you that is not safe.
So if your browser can't support any of the encryption techniques, then it won't display it at all?
Yes. So if I only know certain encryption and the server doesn't have those, it will not make the HTTPS connection. It will pop up an error message. That's why most server administrators want to support a lot of things, because they don't want to lose any customers. And this is just like many things, there's two conflicting pressures. To have the maximum availability, you want to have the lowest level of security tolerated, and your security people would like to push it up, and so you have to make some kind of compromise. Anyway, that's what I wanted to show you. That kind of helps motivate me to care about this course, because I saw that stuff and wondered what it is. And now in this book, more than any previous book I've been through, I'm really starting to understand a lot of this stuff. And this guy is very good at explaining the latest stuff in fairly clear terms. So I'm really happy with this book. So anyway, we talked about encryption for confidentiality, like AES, and then we talked about authenticity with a message authentication code last week. And so now we're going to have the combination of these two. So here's the game. Authenticated encryption gives you confidentiality, and it gives you a tag. This is what's used for financial transactions and a lot of things. So not only do you know that no unauthorized people can read it, that's confidentiality, but you also know that the authorized person encrypted it that holds the secret key. So we'll talk about the types of ciphers that are here, although in reality, there's only one that's a standard, which is AES-GCM. And all these others are alternatives, and like almost everything we've done in this course, there is a standard which is okay but not great, and a bunch of better products which nobody uses because the standard is still considered good enough. And so anyway, so authenticated encryption, there are three ways to do it, although we'll come on a couple more later. You can encrypt and MAC in parallel. You take your plain text and encrypt it to make ciphertext, and then you take your plain text and run it through a MAC function to put a tag on it, and just do those separately. Okay, the problem with this is, we talked about last time, the hash functions that are used for Macs have a lower security requirement than the hash functions that are used for things like putting fingerprints on files to identify them. They are not required to be random in appearance. It is acceptable for a Mac used for a signature to have a non-random output which leaks information about the plaintext because it's supposed to be used with a key. And so this construction, what happens is the encryption might be safe, but the Mac alone might leak information about the plaintext and undo the benefit of the encryption. So the Mac, which was not designed to hide the message, but just to sign it, may undo the benefit of the encryption. And that's why this is considered a poor construction with the typical Macs. SSH uses this technique. It was the original technique. And in practice, it's all right because, in fact, they did not use a weak Mac, which they could have. They used SHA-256, which is a modern Mac. And this is why, since they used a standard Mac that was actually designed for a different purpose and met a higher security boundary, this particular version of this kind of authenticated encryption is in practice secure, which is why, of course, a lot of people prefer to use known trusted algorithms, even if in principle they're overkill. It's often a good thing, and you have all the security of these things. But of course, this means that your security is the minimum of these two. You've done one operation here, and you've done a second operation and put out a second bunch of data about the plaintext here. So if either of these is weak, you've got a weak construction. And that is kind of not the best way to get things done. This would be better. Calculate the MAC and then encrypt it all. Now, if there's something weak about the MAC, you have the encryption to cover it, and that would seem to be better. So this is more secure. And it hides the plaintext tag, so you can't see the original MAC. So that seems pretty good, and that's used by TLS up to version 1.3. But this is considered the best. Encrypt and then MAC. You encrypt it, and then you calculate the MAC on the ciphertext, and now the encryption is white, scrambling the data, and so your MAC can't leak any information about the plaintext, and that's considered very good. That's what IPsec uses, the more modern system, and this is the way it always is. You have the early system, which is just sort of thrown together of whatever components they had, and that became the standard in the old protocols, and as they made more and more better systems, as they developed the cryptographic techniques to analyze what the weaknesses are and carefully patch them, then the later protocols used the more advanced systems. So here's authenticated ciphers. It's more than just combining a cipher and a MAC. You have a key and plain text, and then you create ciphertext and tag. That's the idea. So you encrypt and decrypt. You have to feed in the key, the ciphertext, and the tag, and then you get plain text. In principle, the key and the ciphertext alone would be enough to get the plain text, but it also checks the tag to make sure it passes the authentication test, and it will not return the plain text without that. Otherwise, it's an error saying this is not really an authenticated message. So here comes a chat comment. Okay, do we still need a MAC? Check integrity if you're using HTTPS. This is an argument. In fact, you do get it with TLS, and the book talks about this. TLS does in fact use this system and tag every field. You don't have to. If you don't, which I think SSH doesn't, then what happens is you could, it's not SSH, one of these protocols doesn't. You could encrypt without authenticated encryption and send the data. What will happen though is your server, I can send it a garbled message. I can modify it, and it will waste its time decrypting it and try to use it. It will not know it's been modified. And that is relatively insecure. For example, it's more susceptible to denial of service attacks. I can waste its time sending it garbage that it has to decrypt, whereas if it could look at the tag and recognize this is not authentic, it could throw it away sooner. And also, you can do it without the tag, but it's considered more secure to add that tag. It's another test, like an error detection. Anyway, so I don't think it's absolutely essential, but it seems to be better in practice. All right, so here's the security requirements for this process. The authentication should be as strong as a MAC, and you should be unable to forge a tag for any message. So I should not be able to take, if I have a ciphertext and a tag that I'm going to steal on the adversary, I should not be able to forge any ciphertext that has a valid tag. That's called an existential forgery attack. We have a few of them in the projects. I shouldn't be able to create any message that will pass the test. That's the goal here. The confidentiality should be stronger than the basic cipher, because even if you somehow were able to decrypt it, it still won't pass the tag. You have to satisfy both the encryption and the tag to make it pass, and so it should be stronger in both regards. That's the security requirement. And here's another thing. In practice, it's not enough to just pass encryption, to have data that is encrypted and tagged. You also have to have associated data that is transmitted unencrypted. Because, for example, you might be doing a VPN or some kind of network protocol where you have address information that must not be encrypted because it's going to be used to deliver the packet, but you do want it to be verified with the tag, and that's what this stuff does. So you have a plain text, you have the associated data, and you have a key, and you run it through the function, and now you get ciphertext, the unencrypted additional data, and a tag which verifies that all this stuff is unaltered in transit. That is the actual system that you want in practice to meet real needs for things like VPNs. So that's the game. And this is getting to be a pretty complicated thing to design, and as we'll see, it's pretty easy to make mistakes with it. So here's the thing that might make it even harder. You can have data go through without any associated data. You could also have data go through without any plain text, where you don't intend to have any confidentiality at all. You just want to deliver the associated data with an authenticity tag. So this means you have to satisfy all these conditions. This one is essentially just MAC, and this one is essentially just encryption. But you have to satisfy both of them. And so in practice, you have to add a nonce, because otherwise you have the same old problem that identical blocks of plain text will lead to identical blocks of ciphertext. And in general, they always tell you not to reuse the nonce. But in practice, that is very difficult to achieve. People often make the mistake of reusing a nonce. So after they tell you not to use the nonce, they grade the system on how much it is hurt if you fail and use the nonce over and over again. That is a common measure of the success of your system, how much you really have to live up to that, which is sort of nuts in the world of mathematics. And this is why I talk about the engineering side of this. The math is beautiful, and then there's reality when you actually build devices and hardware where you make approximations. And the real security of the system is in what it is in practice, not just what it is in math, but what will happen when you actually try to do it and you make the usual amount of approximations and mistakes doing it. So a good authenticated cipher should be as strong as the best cipher and as authenticated as the best MAC, and it should not be too fragile if you make a mistake and use the nonce over again. That's the goal. Here's things you would probably like too. You'd like to be able to process it fast. So you'd like to be able to parallelize it so multiple processor cores can run all at once. Counter mode, we talked about this before. Counter mode for, say, AES is parallelizable because the nonce just counts up through something. CBC is not. You have to calculate one block and use that output as the nonce for the next block, so you cannot put it on multiple cores. Then you might want to consider whether you have two layers. AES-GCM, that we'll talk about later, has an encryption function, and then it first has encryption, and then it does authentication. So if you have two layers, you have to finish this before you do that. If you can combine those somehow in one operation, it might be simpler and faster. And then another one is streamable. Do you have to have the whole message fit in RAM? Or can you process one block, throw it away, process the next block? Remember the hash functions like MD5 and SHA-1 were designed this way. You can process one block and update an internal state, then throw it away, process the next block, edit to the internal state, and so on. So you don't really need much RAM. And that, of course, led to the defect of the linked extension attack. If you could catch the internal state, you could start from there and go forward without actually knowing the data before it. That's the consequence of that. So here's the issue. Non-streamable ciphers have to store the entire message because they have to do two passes, like one from front to back and one from back to front. That is a serious problem if you're going to be passing large message blocks through. So other things, sometimes you have to have the associated data before the plain text. Sometimes you have to have it after the plain text. Sometimes you're allowed to put it anywhere, even in the middle. And that would, of course, have an effect on how easy it is to apply for certain applications. AES-CBC have two algorithms, one for encryption and a separate one for decryption. Because remember, the encryption is you run it through encryption and you take the output and use it for XOR. On decryption, the XOR is at the other end. So you have to have two routines, an encrypt routine and a decrypt routine. This might seem unimportant, but it's not a small thing for Internet of Things. If you're trying to put it on cheap hardware and make a million of them, then every routine is using up space on your die, and you'd rather use a cipher that lets you have one routine for encryption and the same routine for decryption. All right, so here's the standard. This is the one everybody really uses, the one that's actually approved, AES-GCM. So take AES and the lowest counter mode, And this is a version of counter mode. The simple counter mode just has the nonce count up 1, 2, and 3. This uses a sort of pseudo-random Galois operation to create those things, and it calculates the authentication tag. This one's the NIST standard, part of the NSA suite, used in IPsec, SSH, TLH, TLS 1.2. This is all over the place. This is the standard authenticated encryption everybody's using. And here's how it works. It's encrypt, then MAC. So you run it through AES with a key. You encrypt the nonce, XORed with a counting number. And then you add the plain text here with XOR. That creates the ciphertext. And then you create the authentication by just running it through a series of these polynomial multiplication operations. This H with the diagonal X is a strange operation, like multiplying polynomials together, which looks very difficult for humans to do, but turns out to be very fast for computers to do because of the modular arithmetic. So the fact that you don't have to carry any of the higher order bits makes it work. So you have a key that's 128 bits, you have a nonce of 96 bits, and the polynomial multiplication is this nonsense, where you have this polynomial times that polynomial, so it expands to all this garbage. And it looks hard for us, but it turns out to be very fast and easy for computers to do. Just a way to combine blocks of data together other blocks of data without wasting any more computer time than you have to do it, or RAM. So this is, the problem with this is if you break the rules and repeat the nonce, it shatters like glass. If you use it even twice, they can deduce the authentication key H, okay, and then they can forge tags. And that is just what the prime rule was not. You should not be able to forge a tag for another message. And if you reuse the nonce, you can do that. So that's probably where they got the attitude that you should really be rating these on what happens if you reuse the nonce, because that's the main failure in this one. And of course, the only reason they invented other ones is because there's something wrong with this one. And that's the thing that's wrong with it. So, and they found hundreds of servers out there, 184 in 2016 with repeated nonces, and 23 servers using all 0 for the nonce, which is why I say, they tell you not to use a nice random number for the nonce. In practice, of course, a certain number of people will not do that. And maybe rather than just yelling at them and saying they deserve to get hacked, you might design a system that can tolerate some level of abuse. It's the encryption and decryption are parallelizable, but the MAC is not, but it is streamable. So that's something. You don't need to hold it all in RAM. All right, so here's one that's faster than GCM, OCB. Developed in 2001, considered very good, faster and simpler. The only problem is the developer apparently wanted to make some money, so he limited it by license. You have to pay him for a license to use it, which is why nobody uses it. But apparently, it really is the cat's meow, lots better. And now, I guess something expired in 2013, or he decided to open it up, so now you can use it for like non-military use or something. But anyway, it's got one layer with only one key. It's very simple. You take each block of plain text, encrypt it with a block cipher, and then you have this offset, and you calculate ciphertext, cipher2, and then you take the last one with a different offset to make the tag. And all these operations are really fast, just XOR and simple operations like that. So the tag is just the XOR of all these things put together, plain text, plain text, plain text, all XORed together, which seemed to me extremely fragile. I personally, when I saw it, I thought all I'd have to do is choose plain text and then have the next block of plain text be the XOR of this one, and it would cancel out, so I could make two messages that would have the same tag. But he thought of that. At the end, it XORs it with an offset calculated from the last block's offset. So it puts something at the end that changes it, I think. So that was the first weakness that occurred to me, but I assume he's thought of that. They say this thing is considered quite strong. There must be a little more to it than that. And anyway, you can also have associated data, and it'll calculate the tag with all these encrypted blocks just XORed together. So it's really just a lot of XORs. Reminds me sort of that stream cipher we talked about before, RC4, I think, which was really just like shuffling a deck of cards. No actual math at all. You just scramble things and shuffle them around. So anyway, it's considered quite good. Repeated nonces don't do much. You'll see occasional repeated blocks of ciphertext matching your plain text, so you'll know that something repeated, but you will not be able to find the key and find out what it was. So it's not too bad. It just leaks out a little bit of data. And it's considered as fast as GCM, parallelizable and streamable. It used to be, on old processors, this thing was actually 3 times faster than the standard, but on modern processors, it's not, because they improved the implementation of it in silicon. And now GCM uses one function for encryption and decryption, but this requires two functions, which might matter for some purposes. So it sounds like maybe that's why he became less picky about the license, because I think the superiority of this method has kind of expired. It's not really much better than the standard anymore. Anyway, then there's SIV, which is another way to do it. This is an authenticated Cipher suite, and this is considered to be secure even if you repeat the nonce twice. So again, all you'll do is you will be able to detect that the same plaintext block occurred twice, but you won't be able to deduce anything further. And it's you have a pseudo-random function with two keys and a nonce. You make a tag with the pseudo-random function here, and you make the ciphertext here. So anyway, it's just a similar mixture. As you see, you just have like 3 or 4 components, and you're just mixing them together in different mixtures to try to dodge all the known problems. The problem with this one is it's not streamable. This seems to me like a really big problem. If you want to encrypt 100 gigabytes of stuff, you have to have 100 gigabytes of storage. So that's annoying. That seems like a pretty serious limitation, enough to make me not want to use it, even if it has other benefits. Then you could use something other than normal ciphers to do this. And this is the plan, not a block cipher. You're just going to transport input to output reversibly without using a key. And this, the book did not describe it this way, but this looks to me like a stream cipher, because the plain text goes in here, and all you do is XOR with bits that come out of this operation, and that's your block of this. And then you put in plain text XOR and put a block here. This is like counter mode. Remember, counter mode for AES uses the AES to create a pseudo-random bit chain, which you then XOR like a stream cipher. And this seems to me to be essentially the same thing. So you feed in this internal state H, and the nonce that comes in, and the key, and you run it through this permutation operation, which just shifts things around. And then you create an effectively pseudo-random bit stream here, which is used to encrypt it. And then you take the last block of the internal state and take some of the bits and call that the tag. So the tag includes input from every block, and all the in-between blocks are just XORed with this pseudo-random bit stream. So it's pretty simple, easy to understand, and decryption is the same thing as encryption, because you just XORed with a bit stream, so you just run the same function, create the same bit stream, XOR it again, and you get back to the plain text. So it seems pretty good, and in practice is considered quite secure. The internal state H is larger than the block size, and you can get tags of different length by just taking a different number of bits from the final internal state and calling that the tag. So you have to be careful how you pad the blocks. If you just pad them with zeros, you end up with an ambiguity where you can't tell the padding from the message, and messages can appear the same. But if you reuse the nonce, nothing really bad happens. All that happens is you have some clue that something repeated in the plaintext, but you can't recover it. And you can't forge a new tag from it. So it's streamable, but it's not parallelizable. You have to, remember there's this construction here where you have to calculate this block and feed it in the next block, and this block and feed it in the next block, like cipher block chaining. So it does not have the virtue of being parallelizable. All right. Anyway, then there's things that can go wrong. You have a large attack surface now. You've got a complicated machine here. Have you seen even an incredibly simple task, like just take a file and put a fingerprint on, like MD5 and SHA-1, turns into quite a mare's nest when you try to do it and not make a mistake. And this is doing a lot of functions. There's a lot of room for error here. You have two things coming in, plain text and associated data. You have to be secure for all values of these, even when they're very long, even when one of them is all 0 or empty. And you have to consider attackers. If you think about the HTTPS attacks like Beast and Crime and Lucky 7, they think nothing of saying, I need to have 1 billion encrypted packets and analyze them all. So you have to consider attackers that are going to do that, have a vast number of message tag pairs. And that's why you really can't just casually say you have to use a different nonce every time. Because if I really harvest billions of encryptions, I'm probably going to have repeated nonces in there no matter what you do. And you shouldn't just shatter like glass if that happens. So ghash is a function used inside AES-GCM, and it actually works like this. You calculate this H value, then you put the H in again and again and again. You raise it to high powers. Now, remember we talked about Pollard's row, where if you just hash something over and over and over, it doesn't just keep changing randomly. It tends to settle into a loop where it goes around in circles. That can happen here. So if you have a value of H that causes a loop, and the loop is kind of short, then this operation, which is intended to make the internal state keep changing randomly, actually moves it around in a loop. And that means, for example, if the loop is like 5 blocks long, then block 6 is encrypted with the same bit stream as block 1. And so you now have, they're going to have, so now you could swap these two blocks, 1st and 6th, and you'd have the same authentication tag because the bit stream used to process them was exactly the same. Now that might sound bad, but that is the kiss of death, and we're doing it in 129S. Here's what can happen. If you have, now this is ECB, where you can arbitrarily swap blocks, but in this other mode, you couldn't arbitrarily swap them the way you can in ECB, but you might be able to swap this one with that one. And if you have a tag used for the web, it might have a series of values and a parameter like this, and you'll have one here that says user ID equals 0. And if I just swap it with this block, now it's going to turn into UID equals 1, which makes me root. So it could be the end of the world that I can just swap blocks and have the tag be accepted. It's really not a small problem at all. However, in practice, there are not very many actual values of H that have short cycles, and there is no way for you to tell what the cycle length is. So he says it can't be exploited in practice. I'm willing to take it on faith, but what I would do, and what you would do in BERT, is you just make it automatically try swapping. Swap 1st and 2nd, swap 1st and 3rd, swap every combination, and just try it and see if you get lucky. And so the real question is, how many of these bad values of H are there? They say that H that's all 0 is really bad, the H that's all 1 is really bad, and there are a few other exotic numbers that are bad. So if they're very rare, then I guess it's okay. The question is, if I attacked a server all day long and had 1 billion tries, would one of them have this property, where I get in someone else's account? And I did not see an announcement in the book of how rare that would be. I would like you to tell me that that is, 1 in a million or something. And I don't know how rare it is. Anyway, so here's another issue. You can have small tags. Remember, it could create a different amount of tags. Typically, people use 128-bit tags, and those are considered very secure. But it turns out that the security of the tag is not like a random number. It's not that if you have a 128-bit tag, there is only a 1 in 2 to the 128 chance of getting an identical tag. It turns out if you have long messages, the message length greatly increases the chance of having another tag. So if you have 4 gigabyte messages with 48-bit tags, you have 1 chance in a million, 2 to the 20, of a forgery succeeding. So if you do use these short tags like 32 or 48, then they are not secure if you have long messages. But if you just use 128 bits, which doesn't seem like too much to me, then you don't have to worry for any reasonable size of a message. Anyway, that's the information here, and I've got a Kahoot, and that's all I have today. Don't have a new project for this class or anything, but we've got quite a few existing projects, so hopefully you've got something fun to do. And if I go to favorites, I should have, oops, I think I forgot to put the Kahoots up again. Yep, I can't do the Kahoots. I wrote them and I forgot to put them in Kahoot. Well, I'm just going to pause the share. I can put them up right now. It only takes a couple of minutes. I'm going to pause the recording, but not the share.